we're going to dive into the technology very, very quickly. I'm going to spend 5 minutes telling you how we started, why we started, what it is that we're building, and then we're going to dive right into how it's being done and why it is different. So when we started, as Mike said, the reverser, we thought not to take the same path as many companies do, build a product, then go out, ask customers what do they want to use it for. We did it the opposite way. The first 6 months of the company, we interviewed hundreds of customers. And we asked them, what does storage look like in your data center today? And what are your pain points? How would you like it to look? All of them, without exception, described this pyramid, which you all know well. Very high performance, very expensive, relatively small systems up top, and the opposite goes down as you get to backup and archival use cases. All of them also talked about the cloud, and all of them agreed that the cloud does not change this basic architecture. You still have the same tiers, you still have the same pyramid. What is the problem with this? Basically, it's complicated. You have to have many different systems. You have to manage all these systems independently. You have to move data around between these systems on a daily basis, from your production database on a tier 1 all-flash system down to your test and dev, down to backup, down to archive, every single day. And you also need to understand which data should reside on which tier, a task that is becoming a lot more complicated. The reason for that is that the applications are changing. Basically, it used to be the case that it was relatively easy to say, this is hot, this is warm, this is cold, we're keeping it for regulatory purposes, but we never really want to read it again. With advances in analytics, what some people call AI or machine learning or deep learning, all of these different technologies basically want that pyramid flipped on its head. They want fast access to the entirety of the data set. The more data you feed into these new applications, the better insights they give back to you. On the other hand, for them to finish in a timely manner, they need fast access to sift through this information, to read it over and over and over again. And so basically, the pyramid is obsolete. Tiering is obsolete. There has to be a better way. And we went back and thought, why is this in existence? The reason is the hard drive and tape before it. Spinning media keeps getting bigger, but keeps spinning at the same rate. The fact that it spins at the same rate means that its performance is stuck for many, many years now. And capacity and performance keep diverging such that that trade-off between capacity and performance keeps increasing. The systems keep changing. Tier 1 used to be 15K spinning drives, now it's all flash. Backup used to be tape, now it's all hard drives. But the pyramid remains because of this basic trade-off. The nice thing about flash is that there is no trade-off. And this is the insight that led to the formation of this company. If we look back at all-flash systems, the first wave of all-flash systems into the enterprise said flash is a lot faster. Let's use it as an acceleration tier. Let's use it as tier 0, companies like Violin, like Texas Memory. Second wave of all-flash companies said flash is not only fast, it's also random access. We can build a new type of system around it that competes with tier 1 hard drive-based systems. Companies like Pure Storage and Extreme IO and SolidFire. The third wave of all-flash companies that we believe is emerging and we would like to lead is based on this insight, that there is no price-performance trade-off. However, when flash is still 20 times more expensive than the hard drive, it's not very interesting. It's a nice theoretical concept that there's no trade-off, but it doesn't help us in practice if we still need to pay 20 times more. In fact, the best way for me to show that there is no trade-off in flash is to look back. When we started Extreme IO 9 years ago, the best SSD you could get had about 5,000 IOs per second. Today, SSDs give you 500,000 IOs per second, 1 million IOs per second. Nobody needs that much performance out of a single device. The reason it goes that way is because capacity grew and performance grew with it. So as Mike said, The only thing stopping us from all flash data centers from getting rid of the hard drive entirely is price. And so we went back and we said, what if we could build a single system that gives you the price of Tier 5, that gives you all flash performance, and in fact, our systems gives you a little bit better than all flash performance because we leverage 3D XPoint, Intel and Micron's new NVRAM technology. And what if we could do this at exabyte scale? Provide an NFS and S3 interface to the application in a very dense form factor. In many cases, reaching more than a petabyte in a rack unit. Once you have a single system that's big enough and cheap enough to throw all your data at it, and it's fast enough such that everything is accessible sub-millisecond latencies, you suddenly don't need to tier data anymore. You don't need to back up data anymore. You can just take snapshots. A lot of things that you needed to do before aren't required, and a lot of applications that were struggling before can flourish with this new access that they have to the information.
You say you don't have to do backups anymore?
Go sorry.
Yes, that's what I said. Basically, when we talk to customers and we ask them, why do you have a separate backup system in the same data center? The response 9 times out of 10 is because it's cheaper. If they could take snapshots and increase the size of their primary storage without incurring the added cost, the disaster recovery implementation that they have in place is enough in order to protect them.
Yeah, I think you're going to get challenged on that snapshots being adequate for backing up.
We haven't so far, but maybe. That's not the
But there's a
main
religious
thing in our
philosophy
story.
that flows around this.
So your assumption
Yeah.
is that there's a DR solution behind that they can take if there's a failure or something like that.
Yes, the assumption is that the disaster recovery is good to treat physical storage problems, and backups are used to treat logical application problems. But that's not where our story is centered.
And Brendan, can I just ask a quick question on this? Your premise is that you're saying that you're using QLC or at least Flash for this, and that the hard drive can't do it. But companies like Infinidat have taken an approach where they say that you can do that, where you can get the performance and you can get the scale. So what is it that's different about using Flash that you're saying that they couldn't achieve in, say, their platform? I'm not asking you to do a competitive analysis.
I can't do a competitive analysis
I'm not asking
because
you
I
to do
don't
that,
know
but
them well
what I'm
enough.
saying is that we can see that the premise of using hard drives and caching in some form does work because they've managed to do it. So why Flash particularly?
I'll tell you what the problem is with caching. Even if you get amazing hit rates in your cache, even if you have 99 out of 100 IOs go to the fast cache layer, you don't get 99% of the performance. Because when Flash is very, very fast and hard drives are relatively very, very slow, IOs are dependent one on the other. They come in columns. They don't all come in parallel. And so when you have 100 IOs and one of those has to go down to the hard drive tier, everyone that's behind it suffers. And so even if you have a 99% hit rate in your caching algorithm, which in many cases in these scenarios is not possible because you're reading from the entire system in a random access manner, and so prefetch doesn't help, and caching algorithms usually don't do a good job. But even if they miraculously did, you still get the lower tier experience when you have IOs that are dependent on each other. And so we believe that you want an all-flash experience. You don't want any IOs going down to spinning disk. And frankly, when we bring down the price of an all-flash system such that it is comparable to that of a hard drive-based system, there really isn't any reason to think about it anymore. There's no downside. And the things that we do to bring that price down such that it is comparable with the hard drive-based system cannot be done on hard drive-based systems. And so it's not that you can pull down that price even lower.
Okay.
And I just want to make one quick point. We believe this is going to be a gradual transition. We believe that VAST is a very viable target for backups. We think one of the biggest challenges that customers are having today are recoveries, especially recoveries of really big databases. When you could throw the performance of VAST at a recovery coming out of a backup application like a Commvault or NetBackup or somebody else, our recoveries are going to be that much faster than what you can get out of today's existing disk-based backup systems.
So eventually, we think you won't need a backup system, but for the time being, we would be happy to be that backup system. Okay, why wasn't this done? And I've been counting the times we've presented this to 500 customers so far. I've been counting the times that customers come back with the phrase Holy Grail, and this is usually the slide where that comes up, and they don't believe. They don't think it's possible. And when we started, we thought long and hard about how to do it, and we realized that they were right. It's not possible. And that was in 2016. And so what we did was, we thought, what if we were in the future? What if we were 3 years down the road? There would be some new technologies out there. And these technologies were already on vendors' roadmaps. 3D XPoint has been on Intel's roadmap forever. NVMe-over fabrics, it has begun going in the right direction, and it looked like it would mature. QLC Flash, even though it's only out late 2018, everyone knew it was coming, and everyone knew that the next generation of Flash will be less expensive and will have less write cycles, because that's what happened from SLC to MLC, that's what happened from MLC to TLC, et cetera. And so we imagined that we were in the future and that these technologies were available to us. And then we asked, what could we build if these technologies were at our disposal? How would we architect a storage system with all of those requests from the customers in mind? And that's what we did. So I probably don't need to explain these technologies to you. I'll give 2 minutes on each, just in case someone isn't familiar with them. QLC Flash, very low-cost flash, 4 bits per cell. Surprisingly, has the same levels of performance as enterprise-grade flash, especially on the read side. As you remember, there is no price-performance trade-off in flash. So why is there expensive flash and inexpensive flash? It's a price-endurance trade-off. The low-cost flash that we use, QLC, has today about 500 write cycles. You can overwrite the device 500 times. The enterprise-grade flash that everybody else uses has about 50,000 write cycles. In fact, if you were to place these devices in any existing all-flash system today, they would wear out very quickly. Extreme I/O system, which I know well, probably in a few weeks even. And so that's not a good idea. However, 3D XPoint storage class memory is here to rescue us and basically enable us to overcome the deficiencies of the low-cost flash. This is a new type of media. Nobody knows how it works except for the people that built it. There are theories on the internet, but everyone knows that it's a new physical substance. Some people assume it's phase change memory. So how can we use it? We use it in 2 ways. Or what is it? It's basically a media that comes between RAM and flash, both in capacity and cost. It's almost as fast as RAM, and it's persistent like flash is. We use it as a very large write buffer, and you'll see why. And we use it as a very large metadata store. Everything we do is intended on building a modern architecture that allows us to bring an all-flash and XPoint system down to the price of your lowest cost hard drive tier. NVMe over fabrics.
Renen, you said use it as a write buffer. What was the other thing you use it for?
Metadata store. We do not do any internal tiering. You said you were religious about backup. We're religious about tiering. We don't like it. And so we don't like the customers
Then you would
doing
call it more of a cache then, right?
Yes, it's not a cache. You never read stuff back into 3D XPoint. We just use it as a space for us to do a few of our algorithms on it, when the data is on its way from the application to the flash.
You haven't mentioned anything about deduplication or anything like that. Is that something that you guys support or not?
We do not.
Stay tuned.
Deduplication. You'll see a slide about that. We don't do compression. We don't do deduplication. We do something that's a lot more aggressive than both of those and works a lot better. Okay, NVMe over fabrics. It's basically a new protocol. NVMe, everybody knows, is a protocol that basically replaces SAS and SATA, a lot more lightweight, allows us to get lower latency into our SSDs, and also runs over PCI Express such that the SSDs can now be PCIe cards. NVMe is not the interesting piece. The over fabrics is the interesting piece. Over fabrics means that we can now access remote SSDs over a standard Ethernet or InfiniBand network as if they were direct attached. In the same way that you could do with RDMA and access remote memory of servers across the network, you can now do with SSDs. And that enables a new type of architecture coupled with storage class memory that could not have been done before, which I will explain right now. But before I explain it, give me 2 minutes on what storage architectures look like until today. And I'm sure all of you will have a lot of opinions, and I'm sure that nothing I say in these 2 minutes will be exact, but it just gives an indication of where we're coming from. So the way scale-out storage has been done forever, and if you look at all the scale-out storage systems, or most of them, I will qualify that, they all have something in common. They're all some variant of a direct attached, shared nothing architecture. Direct attached means that the drives are connected directly to the storage controller, to the nodes. Either inside the node, or sometimes you have 2 controllers connected to a shelf like we had at Extreme I/O, but basically each node can see a small subset of the drives. Shared nothing means that each node has a piece of the pie, or responsibility for a piece of the namespace. And if we're 2 nodes and one needs to access something that this one is responsible for, it needs to ask it for it. It needs to talk to it. The problem with shared nothing architectures is that they don't deal well with failure scenarios. When a node crashes, the entire cluster is now in flux. Everybody is waiting on that node to answer. Everybody is waiting for the cluster to redistribute that node's responsibilities across the cluster before they can answer their application requests. That leads to another trade-off. We're big on breaking trade-offs. We're breaking the price-performance trade-off. This trade-off is between latency and scale. If you have a 50-node cluster, that's OK, because failures will be rare. But if you grow to 1,000 or to 10,000, you're always having someone go up or go down. And when everybody is stuck on that someone, then basically you've reached your scale limit. So you can either do low latency, small scale, or high latency, large scale, when you do shared nothing. Examples of that are Extreme I/O, low latency, a few tens of nodes, Hadoop, batch processing, very, very scalable. Another problem, OK, so that's one concept that exists. In the last few years, people have been going to hyperconverged. And hyperconverged is a very good concept in the sense that it collapses the networks. You no longer have a LAN, a SAN, and an internal storage fabric. You have one network to do them all. It's not good because it couples storage capacity and performance. It couples CPUs with SSDs, with media. And what that means is, it means 2 things. From a performance perspective, you can scale out performance and capacity, but you have to do them together. You have to choose a ratio and stick to that ratio. If you want more capacity without more performance, you can't do it. If you want vice versa, you can't do it. The other thing is, it used to be that hard drives were a lot less resilient than servers. And so if you lost a server, that was a less probable event than losing one of the drives. So it was OK when a server was lost to lose all of that capacity. But SSDs are a lot more resilient than servers. They have a lot less parts in them. They don't have any moving parts in them. So losing all of that capacity inside a server because of the server failure doesn't make sense anymore from a resilience perspective, from an MTBF perspective. How do we fix this? We go to a disaggregated architecture. What does our system look like? Basically, we have 2 parts to it. At the bottom, you see an HA enclosure. It's a JBUF. It's a 2U enclosure. It has a lot of very, very low-cost flash in it, and it has a little bit of storage class memory. Between 1% and 2% 3D crosspoint, between 98% and 99% low-cost flash.
Excuse me. When you talk about low-cost flash, you mean consumer-grade flash or?
QLC. QLC, right?
Not QLC is OK, but there are consumer-grade and enterprise-grade.
When I talk about low-cost flash, I mean the lowest that we can find and put our hands on.
So consumer grade flash.
Today it is consumer grade
Okay.
QLC Flash. Tomorrow it'll be something else.
Yeah, okay.
What we see trending in the flash space is, as I said, lower price and lower endurance. In fact, we've built our system with an assumption of 50 write cycles from the media. So the next thing that comes after QLC, we will be able to adopt. We will be able to let our customers ride that declining price curve that we see in flash today. Which,
The levels of redundancy, knowing there will be such failure.
I'll explain exactly why we're able to do that. We have a few new algorithms that are all based on this new architecture. It'll take me probably another 10, 15 minutes, but
We'll
if
get there.
by
All right.
then I don't answer the question, bug me about it. Okay, what's different between this and a standard JBoF? How it's connected. So we don't have a SAS cable coming out of it. We don't have a PCIe cable coming out of it. We have Ethernet or InfiniBand cables coming out of the back. 4 ports, 100 gigabit each. And so, as I said to you, assuming moderate data reduction, I didn't explain how we do data reduction yet, but we definitely do. We can fit between 1 and 2 petabytes in this enclosure. And assuming more aggressive data reduction, we can fit a lot more than 2 petabytes in each of these enclosures.
So Renen, in the enclosures, is there some sort of additional hardware that does the translation between, you said the fabric was Ethernet? Between Ethernet and the physical PCI that the drives and the SCM are plugging into?
So basically, it's NVMe over fabrics to NVMe is the translation that needs to happen. Today, it happens in software. Not our software, but standard NVMe target software that runs there. Next generation enclosure will either be SmartNICs that do that in hardware, or what I believe, and again, my opinion, is that we will eventually go to Ethernet drives. This was an old idea that was tried. I think it's time to rethink that idea, and you'll see in the architecture why it's very elegant to look at the drives as if they're all attached to Ethernet.
So does that put any limits of scalability on an individual shelf?
Scalability in what sense?
How many drives you can put in it, how much throughput?
Of course. So obviously the amount of drives that you can fit in it is how many we can put.
Yep.
We pack a lot more than anyone else that we know of. But we still pack it in the old form factors, the 2.5 inch. The next generation enclosure that we intend to have is going to be ruler based, so you can fit more in. And as I said, either SmartNIC or Ethernet drives, such that you don't need that software-based translation layer. But all of that is abstracted from us. What we want is Ethernet-connected or InfiniBand-connected drives, both low-cost flash drives and storage-class memory drives. And that is what these containers up top need in order to create the cluster.
Sorry, isn't there an issue? So you want to build a ruler-based JBoF, okay, whatever it is, with consumer-grade flash, but this is custom built because this is an enterprise form factor. So you go a small company like yours, and I hope that you will become the largest customer, but one company is going to Intel and the other producers say, look, we are going to need a special form factor from your QLC consumer grade, and it will add up. First, you are the only one, so maybe you won't find the best price in the market. Second is a custom product, custom hardware, custom
Excellent
product.
question. So what we do when we go to those flash vendors is we draw a very simple picture to them. Today you have 2 flash markets. You have enterprise and you have consumer. Consumer is laptops, desktops, etc. Enterprise is not the enterprise storage market. It's that tip of the pyramid that we saw before. The majority of the enterprise storage market is still hard drive based. That's a third market that you don't have access to. Western Digital does and Seagate do, but the rest of the flash manufacturers do not. And so this is very compelling for them, and they understand it. In fact, if you look at Intel's marketing, you will see something very similar to what we are saying. 3D XPoint is the new RAM. QLC Flash is the new hard drive. So we are aligned in our thinking with the flash vendors. And just in case there will be a form factor misalignment from consumer and enterprise, which, by the way, we have today. Consumer is M.2s, and enterprise is 2.5 inch. There are little adapters built. In fact, we use one in the product right now. We've been using it for a while now, that can adapt between little M.2s into 2.5 inch.
And the requirements from the hyperscalers aren't all that different from our requirements in terms of don't over provision that very much, we'll manage it in the software. So there's some overlap there too. We're not looking for something so different than what everybody else is looking for.
If you were to ask, and that's a very good point, who is closest to us in building such a storage system, the hyperscalers is the answer. Amazon, Microsoft, they're building similar systems. They can leverage the low-cost flash because they have an unfair advantage. They know their application, and they know how they're writing to it. We don't know the application, and our customers don't have the engineering skills of building their own storage systems based on their applications. So we are democratizing this ability and letting all customers enjoy what only the hyperscalers could do before.
So you mentioned there are two boxes. One was the JBoF, and the other one is?
Thank you. Bringing me back on track. The other one is these containers up top. Basically, the JBoF contains all of the state, contains all the fancy hardware, all of the media. The containers are just software. Today we sell them in an appliance form factor because that's what our customers are asking us for. Tomorrow that may change. But they're basically our software in container form factor, and they don't need anything other than a CPU to run on and some memory in order to hold their data structures. Obviously, they also need connectivity into these enclosures. And so a cluster is built out of a set of these containers and a set of these enclosures. And you can grow them independently from each other. The nice thing about all flash systems is that the performance bottleneck is almost always up at the CPU. You have so much performance coming out of the flash devices that you never run into an issue of having that the performance bottleneck. And so CPU is our performance bottleneck in our system. And what this lends itself to is the ability to grow capacity independently from performance.
What's the protocol between the container and the host?
Between the container and the host above it, today we support NFS and S3, and we intend to add more protocols.
NFS and S3.
Correct. We started with those two because those were the most prevalent in the market segments that we're going after first. But that's an interesting question. 1 second.
Huh?
Why do we have all of these different protocols? It again goes back to that trade-off. Block was always fastest. File is most convenient, and object is the most scalable. But if you can build a single system that's as fast as block, as convenient as file, and as scalable as object, you don't really need all of those protocols anymore. Not to say that we won't implement them. We don't want to re-educate our customers. But many times when customers say, I need to move from file to object because I'm hitting these barriers, when they put this system in, they don't need to do that anymore.
You haven't mentioned how your data reduction is done yet.
I
Where is the data reduction done in this architecture?
That
You got
would
the
be the
JBoF?
last-
Patience, Ray, patience.
Please.
Okay. That I will answer. It's not done. It's not done at the JBoF level. There is no logic down at the JBoF level. All of the logic is up here, and all of the state is down here. And that is
What handles the intelligence to move data from the SCM to the QLC Flash?
up in the container. Everything is up in the container.
But it's not tiering.
It's not
That's what he
tiering at all.
said.
It's not
That's what he
tiering.
said. I agree.
We
So far.
move it.
And it's not a cache, which is the other thing he said.
Correct. Why is
a
everything
buffer.
up here? Everything is up here for two reasons. The first reason is if I were to put logic down in the enclosures, that logic may hurt my performance. I may move the performance bottleneck down into the enclosure. I don't want to do that. We want always to be able to add enclosures only when you need more capacity, add containers or give our containers more CPU cores only when you want more performance. But the more interesting reason is all of our algorithms are global in nature. When we talk about data reduction, which I haven't yet, it's global in nature. When we talk about data protection, it's across all of the SSDs in the system. When we talk about data placement and our ability to use QLC Flash, it's across all of the devices in the system. And if we were to put any type of logic in the enclosure, we would hinder that benefit that we have.
So I imagine that this translates as well to a truly cloud version. Obviously, containers are going to do that quite capably, right? So the compute layer or the container management layer makes a lot of sense to me. How do you make an equivalent, though, to the storage side of the equation in an open S3 environment or a blob environment, something like that?
Are you talking about Amazon's public cloud, or are you talking about cloud architectures? Because those are different.
So I'm talking about in a cloud environment, an AWS, for example.
So in AWS, you can't do this today because
Exactly.
you don't have these hardware pieces.
Correct.
2-3 years down the road, you will have these hardware pieces in there.
Yeah, they're moving to a potentially available bare metal model.
Correct.
And-
And then you will be able to sprinkle our software on top and just use it in the public cloud. Today, that's not possible. We do see a lot of customers, and Jeff will talk about this later, leverage the public cloud with our system. But the nice thing is that this is built with cloud concepts in mind. So
Absolutely it is, and I can see that. What you're going to sacrifice, though, in a cloud environment is the kind of performance that you are used to when you're running this, even as an object-based storage environment on-prem.
that is true unless you have access to what their developers have.
Which would not be an AWS or an Azure environment, but you could do it in a
That is
a hosting provider, for example. Yeah.
For our customers, what we see over the last 3 years that we've been talking to them is that when you have 50 terabytes or 200 terabytes, ship it out to the public cloud, don't manage a data center, don't have a team in place, makes a lot of sense. When you get to tens of petabytes or hundreds of petabytes, or some of our customers have crossed that exabyte line, that doesn't make a lot of sense anymore from an economical perspective. You have,
I think it doesn't anyway.
well, then you're on our side. I'm going to move to this side now. No. Okay, so disaggregation is key. But what we found was that disaggregation is not enough. Once you have this disaggregation in place, you don't need shared nothing anymore. You don't need to give each of these containers a piece of the pie that they are responsible for. They can all see the entire namespace as if it was direct attached. And that allows us to do the really interesting things. For example, in the synchronous path, when a container gets a request from an application, whether that's a read or a write or a metadata operation, it does not need to talk to any of the other containers in order to serve that request. It just needs to read and write from this storage class memory in Flash across the fabric. That allows us to scale up to levels that weren't possible before. When one of them fails, nobody else cares. They're not talking to it, they're not stuck on it. Only in-flight IOs to that container even notice that something happened, and those will get resent to another container because they can all serve all of the requests just by reading and writing to this single point of truth.
The containers don't contain any metadata? Containers
They
don't
do
contain
not.
any state?
None. They're completely stateless. And that is very, very key. I'll talk a lot about that in a minute.
So does that mean
I'm sorry. Go ahead.
that means you need to somehow lock the metadata that's sitting on your persistent storage, whether that's SCM, but you still need a locking mechanism that can coordinate reads and writes between the containers, even if they don't hold that state.
So what we have, and this is a big piece of our IP, and I have another slide on this, is how do the metadata structures, what do they look like on storage class memory? This is a new paradigm. It's not like memory, because with memory, when everything crashed, you don't care what it looks like anymore. Here, we're sharing this memory across 10,000 containers. If one of them crashes, it needs to remain consistent for everybody else. What that means is that a container needs to be able to crash between every 2 lines of code, and that metadata structure needs to remain consistent. What that also means is that Basically, we need to build a way such that each of these containers independently read and write to this storage class memory without contending with each other. And so our metadata structures are built such that 10,000 containers can read from them at the exact same time without locking anything. They can do that at the exact same time that someone is writing the information, and they still don't need to lock anything. The only case that we need to handle is when we have two writers writing to the exact same location.
Yeah.
And the way we fix that is by having one more piece of media in this HA enclosure that's not up here. It's a little bit of RAM.
Okay.
And we use that RAM, we basically do atomic operations, atomic RDMA operations, to grab a lock or to release a lock.
Okay.
And that only happens when someone wants to write somewhere, and there's only contention when two applications want to write the exact same byte in the exact same file, which is something that almost never happens. And when it does happen, you absolutely want them serialized one after the other.
Okay.
So when you talk about thousands of containers,
Yes.
you mean many containers for each single node in the front end, right?
I mean, no.
No. So you mean each single container in a single front end node?
I would not put more than one container in a node. There's really no point to that. You have two options. You can put a container in a dedicated server, and then it's a file server or an object server the way you're used to. Or you can put this container inside the same physical server as the application. And that is where its statelessness comes in.
But I don't know. So each single container has a specific function, right?
No.
So
They all do
each
everything.
they do okay.
They all do
the same operations.
Correct. They're exactly the same. And they don't communicate with each other in the synchronous path, so they're loosely coupled, and you can have tons and tons of them without ever worrying about that.
Okay.
So you can lose all of these containers because they're stateless, and you didn't lose any data at the exact same moment. You can lose all of them except for one. You still have access to all of your data with no recovery code that needs to happen because there's nothing to recover. The data is exactly the way that it's supposed to be. But the statelessness allows us to base this on containers. And the interesting piece happens when we start mixing the containers in the same physical servers as the application. What are the advantages to that? And everybody's been talking about software-defined for a very long time. Customers love the idea of software-defined, but they hate software-defined products. They want to buy an appliance. 9 times out of 10, they will want to buy an appliance. The reason is that software-defined is hard to deploy, and it's very inefficient. So when you take in the cost of the hardware and the software, it becomes more expensive than buying an efficient appliance. We think that using this architecture, you can solve both of those problems, and you can enable a new software-defined world. And there are a lot of advantages to software-defined. Namely, if I put a container inside the same physical server as the application, that NFS client and NFS server communication is a loopback event. It is not going over the network. So there's no TCP going over the network anymore. It's just parallel NVMe down to the HA enclosures. Another thing that you get from it is, let's say you have a 1,000-node cluster, compute cluster, and you upgraded that to 2,000 nodes. You doubled your compute performance. Now you have to rebalance, you have to get more storage performance such that it matches. No. If you have a container of ours in each one of your nodes, you just doubled your storage performance as well. And you didn't have to buy more capacity to do that. If you want more capacity, buy more capacity. But if you don't need it, why pay for it?
Brendan, does that mean, for example, if you had a client server that was running an application, you could run multiple NFS clients or your clients, almost like one to serve every single application and scale out on an individual server too?
You could.
Microfile server.
Right. Okay. So you could run multiple microfile servers on the same physical server in order to scale out the
And
access.
you could also do the opposite of that, which is give this application these containers to work with. Give that application these containers, or this department, and you get very, very good brute force quality of service because the performance is bottlenecked on CPU. And so they don't even know that they're accessing the same shared consolidated storage device anymore.
Are you saying that the performance of your system scales linearly with the number of containers?
Super linearly. We'll get to that.
Super linearly. It's the second time I've heard that phrase today.
Is it?
Yeah.
Well, I apologize for being after the people that were.
Okay.
So just to clarify, this is very similar to, I remember the E8 architecture being that they had their client software, being able to open up all the threads over NVMe directly, and they wanted scaled performance, you just assign more CPU. So we could scale this by container saying, I want to give you X CPU cores
You
on
can.
my server, or I can say I want 4 containers instead of 1 container with 4 cores.
You can. You can do both of those. Big difference is we're not exposing NVMe up to the clients. We're exposing file systems. We're exposing object stores. We're making it very easy for our applications to access this storage, even though they get the benefit of parallel NVMe.
Okay.
And many times we get compared to parallel file systems. People don't like putting a little thing inside their kernel, a proprietary file system. They don't like managing software and updating it. It's very messy. It gets very complicated. Now, you can just add another container, completely separate in a logical perspective, but inside the same physical server. You get all the benefits of a parallel file system with none of the complexity. And then some people ask, but what about TCP? That's only limits you to 1.5 gigabytes a second. So there's an old thing also that people haven't used for a long time called NFS over RDMA. And when you do NFS over RDMA, you break that limit. You can do 6 gigabytes a second. You can do more than that. And that is especially important in these new types of applications like AI, where you have hungry GPUs that want a lot of data. And so you get all the benefits of parallel file systems without any of the drawbacks using this mechanism.
So, Renen, presumably you can create a container that becomes the protocol. So you can do your object, your NFS, your block, your Hadoop, or whatever you want. And I guess that's how you're going to implement multiple different file protocols. Or
Yes, and we have a slide for that as well.
And the other thing is that you're using the word container to be both software specific as well as an appliance. Are you actually a Docker type container?
Yeah. When you buy an appliance from us, we put our Docker container inside a standard Intel server. That's all we do. And the nice thing is that basically, okay, I had another thought. The way we envision the data center, if you imagine the way software-defined networking worked, and software-defined networking was a huge success, software-defined storage, not that big of a success. Software-defined networking said, I'm going to take all of the logic, all the intelligence out of the switch, put it on a standard Intel server. But they still have that top-of-rack switch, which usually is placed at the middle of the rack for cable length purposes. It still has that dumb switch that actually does the switching, the packet movement. Software-defined storage, we didn't try that. What we said was, they didn't daisy chain all of the servers and said, we don't have a switch at all. They did that. What software-defined storage says, let's stick the storage inside the servers. That's not the right thing to do. The right thing to do is every rack that you have in the data center, put one of these JBOFs in it. It's an Ethernet-attached JBOF, and the rest of your rack is servers. Those servers run your applications, your databases, your software-defined networking, your software-defined storage. We believe they will run all of those in different containers as other companies are.
And you mentioned the JBOF is 1 to 2 petabytes. You haven't talked about whether that was effective capacity after data reduction or before data reduction.
It's after moderate data reduction.
Moderate amount of data reduction.
Raw capacity is 600 today? 600 terabytes.
If that's not enough, just buy 3 or 4.
Yes, you can buy as many.
Why
as you
stop
like.
there?
Renen, can I make one quick point? So this is near and dear to my heart. When I was running primary storage at EMC, I got a daily report on data loss, data unavailable around the globe. And if you ask me for a percentage, I would say 95+% of the time that issue was driven from writes landing in DRAM and battery backups, and something occurred, and a controller failed, or there was a power outage, and the system had to try and ride through, getting the data that was sitting in DRAM destaged down to a persistent data store. We've broken the trade-off around resiliency. Nothing ever lands in our system on anything volatile. It lands in persistent memory 100% of the time. So that's a big difference from a resiliency standpoint. We don't have battery backup units. We don't have to worry about all the HA code to destage down and get down to a persistent data store. As a matter of fact, one of our biggest customers challenged us in our HA testing and flipped the PDUs while they were hammering the system, and they brought it back up and the whole system recovered. Everything was just sitting where they left off.
This is a much more resilient architecture by design. Again, not possible with older hardware components. And you asked about cloud, the public cloud. So there are a lot of concepts that we borrowed from the public cloud. For example, are you familiar with pets versus cattle? Yes. Okay, so old systems, most of the shared nothing systems that are out there today, are pets. Each node matters. We care about it. We want to keep it up. We want its hardware to be stable, because when it goes down, there's an event. Something needs to happen. Here, they're all cattle. They're all stateless. They can fail. They can go back up. And the nice thing about that is that you can not only scale performance independently from capacity, you can now scale performance dynamically. Let's say you want more CPU power overnight. Shut down all of our containers. You want more storage performance during the day. Spin them back up. And you can do that. You can do that as you would like with no effect on the cluster. Yes. Yes. And when you lose 1 out of 1,000, you lost 0.1% of your performance. When you lose half of them, you lost half of your performance. It scales up and down.
Yeah, but the deployment onto fresh, you lose 1,000 of your 2,000 containers, you create new deployments like that. I imagine it's a no-brainer to.
There's no metadata that needs to be pulled up. There's nothing that needs to be hydrated. Everything is, as you say, instant. I wish I could do that. Fingers. Okay. So, what does this mean from a file system perspective? Old file systems had a lot of constraints about how big files could get, how big directories could get, how deep the directory tree could get. We don't care. Our metadata structure, as I said, lives in storage class memory. It lives in 3D crosspoint. And it's built like a very wide fan-out tree. The reason it's always consistent is because when you make changes to it, you make them on the side. And when you flip them into the tree, that's an atomic operation. That's why you can crash before or after and still remain with a consistent metadata structure. Another nice side effect of this very wide fan-out tree is that every level is a lot bigger than the level above it. So if we run out of metadata space in storage class memory, we spill into Flash. And we'll never run out of metadata space there.
Or like peering almost.
It's
Just saying. Just saying.
You're keeping me honest. Basically, the lowest level of our metadata tree is on Flash. The higher levels are on Crosspoint. So when we have, let's say you have 1 trillion 10-byte sized files, you can do that. Metadata takes up more space than data, but you can do that because of the way this is built. You can have one file that's 100 petabytes in size, and you can do that. You can have one directory that's 1 trillion files, or you can have a lot of very small directories. Our metadata structure will always look the same. And the reason is that we splice everything up into small pieces regardless of how big it is. That's the opposite of what you wanted to do when dealing with hard drives and even when dealing with Flash.
Is your metadata replicated across all the JBOFs? Or is it sharded or somehow? Or?
So everything is, the containers, what they see is drives. And in all cases except for one, they don't care which JBOF the drive is in. They just see, if you do an LSPCI on one of our containers, you see a long list of devices that they can handle. The only case where they do care, where they are what we call topology aware, is in the resiliency scheme. And they will attempt to break up across as many failure domains as they can, such that when you have enough of these enclosures, you can lose a full enclosure, even though it's highly available. Once you have 30 or 40 of them, you can lose a full one because there's enough redundancy in the system. We'll talk about that when we talk about the data protection scheme.
Renen, you didn't answer me.
What was
Is the metadata replicated across all the JBOFs, or is it split up and sharded across the JBOFs?
Both. It's not replicated across all the JBOFs, by no means. It is sharded, so each device, it's not across the JBOFs, it's across the devices. So each device has a piece of the metadata. The way it works is we have these trees, and so the root of the tree is built on what's known as a consistent hash function, such that you can add more cross-point devices and remove cross-point devices, and the containers just need a function to understand where the root of the tree that they need resides, which container it's on. And then once you find that root, everything else is with pointers. So that tree is basically built by pointers, and they point to other areas in the distributed system. It doesn't have to be a pointer to the same device. And we can do these multiple accesses to cross-point because it's so fast. It's about 5 microseconds of latency of cross-point, a couple more for the network. So around 10 microseconds of latency, you can do a round trip. You can do 5, 6, 7 of those easily while still maintaining sub-millisecond latency up to the application.
I didn't understand. It's replicated anyway because.
I didn't answer the second part of the question. You're right.
No,
You're
yeah,
right.
you answered only the
question.
sharded part.
No, the metadata cross-point is triplicated across systems, and Flash uses our own proprietary data protection mechanism, which I will explain. Okay. The last piece of it is everything is self-describing. And I think I have a slide for that. What does this mean? Basically, in old scale-out systems, everybody asked, well, what do you do with locking? That's a central process. You need someone to manage that. What do you do with metadata? You need a name server to manage that. That inhibits scale. We don't have any of that. In our system, there is a single source of truth, which is the media itself. And everyone can read it whenever they want to. And so locking is just another attribute of a file. In fact, we don't have a file system internally. What we have is an element store. We chose the term element because it was the one we could find that wasn't used by anyone. But basically, an element can be a file, it can be an object, it can be a directory, a bucket, and if we want to add block in the future, it could be a volume. It has two pieces to it. It has attributes and it has data. And for example, a file will have both. A directory will only have attributes. It won't have any data. And so this is a superset in terms of semantics of all the protocols that we intend to support. Okay. What does this mean? Well, first of all, it means that the protocols are all side by side. They're not stacked on top of each other. A lot of people ask us, well, what is it internally? Is it an object store? It's not an object store. It's this element store. And so you can put all the protocols one next to the other. They all get native performance to the element store. The other nice thing about this, a side effect, is that they can read and write the same data. If you wrote a file through NFS, you can read it through S3 or vice versa. And as we add more protocols, that will remain true. But the real interesting piece is the self-describing nature. Basically, for each element, we have a key value store. And that holds attributes. It can hold the size of the element, how much data it has. That's an internal attribute. It can hold ACLs. It can hold user metadata in the case of S3. And it also holds the lock state and the snap state, et cetera. And so when we lock a file, we just update its attribute. And when somebody else wants to access that file, it just checks if it's locked. And so there's no lock manager. There's no central entity that needs to manage these things.
So that's one of the key attributes you get out of the fact that inversely from all the old scale-out systems, you're shared everything as opposed to shared nothing.
That is correct.
So that nothing was meant we had to put the everything somewhere else. Okay.
And each one of the elements has a data store, which is very capacity efficient. Everything in our system is byte addressable. So Crosspoint we treat as a byte level store. Flash, we do very large chunks, but internally we treat everything as if it's byte ranges. And so it's thinly provisioned very, very efficiently. And it's scalable across the entire system. In many systems, things are scalable across the entire system, but you need to have the different pieces evenly spread out. In our system, that's not the case. If you have a 2 petabyte JBOF that you bought today, 5 years from now, you want to buy a 10 petabyte JBOF because that's what's available, you can add it to the same system, and the system will distribute the data according to the amount of capacity on each of the SSDs. The same is true for the CPUs. If you have weak CPUs running today, the containers, 5 years from now you have stronger CPUs, then the system will distribute the load according to the available CPU resources, not evenly across everyone. And that, again, is something that we can do because we disaggregated compute from capacity. Once they were coupled, you wanted more capacity, you had to get more CPU power in there because otherwise you have a bottleneck. It's a famous thing that in scale-out systems, if one piece is slower than everybody else, then the available performance of the system is that piece times the number of pieces. That's not the case here because we spread everything according to the available.
Can I just ask, to extend on Eric's question just a second ago? Yeah. It sounds to me that what effectively happens is the containers at the very top, every time they do any sort of action, like a read or write of a file or something like that, they're effectively walking a tree of objects to do that task. So they don't maintain any real state simply because every action starts from a root and goes down to an object read
Yes.
or an object's write
That is
across those objects.
There's no
They
metadata.
They build a view of a file based on that every time they service a request. Okay.
There's no metadata caching at the containers?
None. If we had metadata caching in the containers, we would need to build cache coherency mechanisms.
Yeah, but
That would limit our scale. Flash is fast enough such that you don't need caching, and we would much rather have high scale and simplicity rather than give you a few more microseconds.
And you mentioned earlier that the performance of the system scales based on the number of containers. Does it also scale on the number of JBOFs?
So
Or the number of devices?
There is a limit. It's not a practical limit. There is a theoretical limit where if you had 1 million containers on one JBOF, you would be bottlenecked on the network probably. But you usually don't get there.
And you mentioned super linear.
I'll talk about that as well.
Sure.
That's on the data protection slide. If I forget, remind me.
He will.
Mike will remind me. Okay, I think that's all I had to say on this. But everything I described didn't say anything about how we get the flash down to the price of hard drives. It's a modern architecture. It gives us a lot of benefits, but it's still based on the most expensive media out there, 3D XPoint, on the most expensive networking out there, NVMe over fabrics. How do we get this down to archival price points? And that is based on one thing. That shared everything approach means that each one of our containers can see the entire namespace as if it was direct attached. We leverage that intensively. We do 3 things in order to leverage that. The first is we use the lowest cost flash. And I'll show you why we can use the lowest cost flash due to that architecture. Second thing is we don't waste any space. Existing storage systems waste space on metadata and on redundancy. You'll see how we solve that. The third thing is, if you'd like to hear this one, data reduction. And I'll tell you how we do it. QLC Flash. As I said, QLC is the latest flash that's out there. We're not designed specifically for QLC, but we are designed for very low endurant media. Less than 500 write cycles, as I said before. We don't need more than 50. Why don't we need more than 50? And it took us a long time to understand this. And at first, when we started the company, we thought we could only build an all-flash archive because archives keep the data for a long time. And we said, okay, the low-cost flash doesn't have a lot of write cycles. Maybe we can do an all-flash archive. And the code name for the company was random reads because we could do a lot of random reads, but the writes are limited because of the low-cost flash. We realized that's not the case. We also realized that unstructured data is moving to a world where things are getting written, kept for a very long time, many cases kept forever, and read over and over and over again because of these new analytics applications. And these are new data sets, and these are existing data sets. Storage admins are being asked to monetize existing data, to make money off it, to gain insights from it. But it's all on archives. They can't really do anything with it. OK, so what was the insight that led to us moving from an all-flash archive to collapsing the entire pyramid? That insight is that write cycles, or endurance, is very easily amortizable. If you have 50 write cycles and you're keeping something forever, that cell has 49 leftover write cycles. And those can be used for more dynamic applications. If you have 100 petabytes of archival data and 10 petabytes of data that overwrites itself once every 6 months, and a petabyte overwrites itself once a month, and 100 terabytes that overwrites itself 10 times a day, the average is what matters. And it's a weighted average. So the static applications lend a lot of extra write cycles to the more dynamic ones. And that is why we can collapse the pyramid. That is why we don't need more than 50 write cycles. The other piece of it is that when it's a virtuous circle, when you collapse the pyramid, you don't need to move data around anymore. The reason you moved it around is because this was very expensive. You needed to free up space to bring the hottest data in. But before you deleted anything, you moved it down to a lower tier. Now you're not moving anything down to a lower tier. You're just keeping it where it is. And so inherently, you need a lot less writes. However, why do these guys wear out so quickly? They do have more than we need. They have 500 write cycles. It's not that the application needs 500 write cycles. It's that existing storage systems have very high write amplification. Write amplification comes from the drives doing garbage collection. You can't write to NAND in 8 kilobyte chunks. You have to write to it in erase blocks. And so when an application overwrites in small pieces, the SSD needs to garbage collect. It needs to free up large pieces. And over the lifetime of a piece of data, it can move 50, 100 times, causing write amplification of 100x. So when you have 500, and you have 100x write amplification, then you only have 5 write cycles up to the application. So our mission is to eliminate write amplification. And I'll tell you exactly how we do that. Other cons of the low-cost flash: it's not dual-ported. There's no power protection. Write speed isn't very deterministic because it has crappy controllers in there that don't do a very good job. We overcome these with Crosspoint. The poor write speed is overcome by basically putting everything on Crosspoint and migrating it off to flash in the background. So the application gets Crosspoint latencies. And the flash has plenty of bandwidth. It's just concurrency issues and latency issues that we need to deal with when writing to it. So we control the writes. No power protection. We land everything in Crosspoint. We don't take it off of Crosspoint before we are assured that it landed on NAND, on persistent. Not dual ported. That goes back to that conversation that we had before about adapters. Basically, all of this media is NVMe, and so you can use the little PCIe switch to cause it to be dual ported. Whether that's in an adapter or in an enclosure, that's something that can be done. But the write cycles are the hard piece. And this I think we covered.
Sorry to interrupt again. Of course, you said you were going to be addressing the data
Reduction in that last, that's what you said you were. Okay.
Last slide.
Just want to hold you to it.
If Jeff starts talking and I didn't address it,
Okay, fair enough.
then drag me back out here.
We'll get there, Matt, I promise.
How do we deal with write amplification? Basically, we don't let the drive deal with it. We write to the drive in full erase blocks, and what we call super erase blocks. 4 gigabytes is the size that we use. And then it doesn't need to move anything around because it either has an erase block that's completely written to or completely free, and it basically can only do one thing, which is fill that free erase block every time we write a new one into it. But basically what we did is just bring the problem up to our level, because the applications are still writing in small chunks, and how do we handle it? And why can we do a better job than the SSD could? So the reason we can do a better job is because we have this global view. First and foremost, because we have tens of thousands of devices that we're looking at, not just one. And because we have much beefier CPUs, not those crappy controllers inside the consumer-grade flash. But that's not the interesting piece. The interesting piece is we have visibility into the file system and the object store. We can see the file type. We can see the directory structure. If this directory keeps getting overwritten, it's probably a temp directory. If this directory gets written to and never overwritten at all, it's an archive directory. And we have historical patterns at the file and object level, what we call the element level, that we keep as part of our metadata, such that we understand when pieces are expected to be overwritten, when they're expected to be deleted. Why is that interesting? So take an erase block and bin them. Let's say this erase block is 1 day. This is 1 week. This is a year. This is forever. We take all the data pieces that are expected to be overwritten in a week from now, put them together in the same erase block. We come back a week and a day from now, it has been naturally invalidated. We didn't need to move anything around. We have a full erase block to work with. So first time around, this wouldn't work very well. We don't have the history. We haven't trained yet. Second time around, we'll do okay. Third, fourth time, we know what's going on and how to do this. We call this predictive placement. That is what allows us to use the low-cost flash. However, the low-cost flash, even though I call it low-cost,
Low cost for flash.
is still expensive. It's still more expensive than the hard drive. And so we need to do more than that. Second thing we do is data protection. And this is where the superlinear piece comes in at the end of it. Global data protection. As I said, we do everything globally, and that is our advantage. How is data protection done? You have a trade-off, and we like breaking trade-offs. You have a trade-off between resiliency and capacity efficiency. You can do triplication. You keep 3 copies of everything. You wasted almost 70% of your capacity, and you're able to sustain 2 drive failures. When the third failed, you may be in a data loss event. So that's an extreme example. Various different types of RAID schemes have been suggested over the years, and erasure codes, but they all have this trade-off between capacity efficiency and resiliency. How do we break this trade-off? The answer is very simple. It's surprisingly simple. Very wide stripes. Instead of doing 4+2 RAID 6 or 8+1 RAID 5, we do 150 plus 4. And that's how we start. And as the system grows to more and more of these enclosures, the stripe sizes grow with it. So imagine 500 plus 10. As we grow, we add more resiliency. In the first example, you could lose 4 drives at a time. In the second example, you could lose 10 drives at a time. And we pay less in capacity overhead. First example was almost 3% overhead. Second example is 2%.
And the CPU overhead for calculating this part?
Yeah.
I will talk about that. I will talk about that. Why wasn't this done before? That's the main reason.
That's probably because there's a hidden way of doing this better than we all thought of.
That's
A
the
log
main
structure
reason.
file in the back end?
There's no log structured file for that. It's all erase block based, so it's not a log. But I'll explain exactly what it looks like. Why wasn't it done before? The first reason is shared nothing architectures, direct attached. I could only see 10 drives. I could only see 20 drives. And building a distributed RAID scheme is hard to do. Not impossible, but very hard. We don't need to do that because each one of our nodes can see all of the drives as if they are direct. Second reason is if I have 500 plus 10 and I have an update, I need to update all 10 redundancies because they have data that's dependent on the data in there. That increases write amplification, reduces performance, both bad things. We don't want to do that. So we need 3D crosspoint. We never do an in-stripe update. We always write full stripes the same way we always write full erase blocks. And in fact, our stripes are dynamic in size and also in the way that they're built. So we can just take up a bunch of free erase blocks and build a new stripe whenever we need to. That, by the way, is why we can also deal with different sized drives because we don't really care about the drive geometry. We just care about erase blocks inside that drive. A larger drive will be present in more stripes than a smaller drive. And why do you need 3D crosspoint? Because they're very large. Imagine 500 wide, 4 gigabytes high. You need those bins. You're in the tens of terabytes range that you need in terms of space before you're moving off to the flash, and so you need crosspoint for that. But the interesting question is the one that you asked. What happens when a drive fails? If I do Reed Solomon or any other erasure code that is in any other storage system, what I need to do in that case is I have 500 plus 10, a drive failed, I need to read 500 drives or an equivalent of 500 drives in order to recover. That's not good. What we did was we took the extra redundancy, and look at this. You're using only one of the 10 redundancies that you have. You're ignoring the other 9. We're taking all 10 redundancies, and we've built a new type of erasure that can leverage those even when we didn't have 10 drives fail at the same time. When we have one drive fail at the same time, we leverage those 10 redundancies to read less. And in fact, we can leverage them significantly to read 500 divided by 10. Only the equivalent of 50 drives needs to be read. And if it was 500 plus 20, it would have been 500 divided by 20 that needs to be read in that case. And so this is a new type of math that is enabled because of 3D crosspoint and NVMe factors.
Did you just announce we invented new math? Is that what just happened?
I'm pretty sure that's what I heard too.
New math, yes. In fact, funny story, when we started, there's a thing called regenerative codes. And I was sure, having not read the actual papers, that regenerative codes does exactly what I just explained to you, which it does, but at small scale. And so I told the developers, go read these papers. That's how we need to implement our data protection scheme. And they came back to me a week later. They understood this after a day, but they were a little bit not sure. I am the CEO. They came back a week later and said, you don't know what you're talking about. These papers are nice, but they're not practical. They break down after 10, 20 drives. You can't build 1,000 wide stripe using these mechanisms. And I told them, okay, I hired you because you're smarter than I am. Go figure it out. And that's what they did. So that's why we needed to generate that new math and couldn't take something that was existing on the shelf. Where does superlinearity come in? So as you see, the bigger the system is, the less the capacity overhead. The bigger the system is, the more resilient it gets. When we talk about data reduction, you'll see that the bigger the system is, the more data reduction gains there are to be had. So as a system grows, it likes to be big. In fact, in QA, when we were smaller and had less money, we worked with smaller systems. A lot of the bugs that QA found were simply because the system was too small. It likes to get large.
So what's the minimum size of a system?
We start from a petabyte.
And
You really want?
Yeah, number of nodes, number of devices. What's the minimum on that?
We don't care. You can have as many devices as you want. You can buy them from us. You can just spin up containers.
The typical initial customer is one data node and 4 compute nodes.
Okay.
So 1 JBOF and 4 containers. And that's a petabyte-ish?
Yeah, with reduction, that's a petabyte. It's 600 terabytes before, so
Yeah.
petabyte and a half, 3 petabytes, depends on your use.
So now all of the capacity goes up to the application. We don't waste space on redundancy without needing to face that trade-off against resiliency and against rebuild speeds. We broke that trade-off.
Hey, Renen, make sure you hit what Ray asked earlier about how the data is sitting in Crosspoint and how we chronologically apply, the erasure coding and the data reduction before it.
So if you look at the write path, you write something, the application writes something, we landed on Crosspoint. The application writes another thing, we landed on Crosspoint. Then we have a migration process. Once enough things have been written to Crosspoint, we run our predictive placement algorithms, we run our data protection algorithms, we run our data reduction algorithms actually before those two, such that everything is placed on flash once. You never have to move data around. the last thing I wanted to say here, again, borrowing from the hyperscalers, is that everything is fail in place. If a drive fails, you don't have to rush into the data center and replace it. You can keep it there. You just lost a little bit of capacity. Everything will regain full redundancy very, very quickly, and you can live without that little piece of capacity. You can go into the data center every 6 months, every year, add more capacity, that's what we like because that's what we sell, and replace the
So what you're saying, though, is that on failure events, you don't go into a rebalance, or you're not, again, you're eliminating that write amplification issue of the rebalance on a lot of
The
evenly
reason you
distributed
needed
clusters.
rebalance in scale-out architectures is to get performance. When you had a new node, you had to make sure that you're moving data onto it to get its performance. When we add capacity, it doesn't matter if you use it or don't use it. The performance is limited by CPU. And so you don't need to do that rebalance. The way we write, we always write disproportionately to the SSDs that have the most free space in them. So naturally, everything will get filled up. In the same way, we always give work to CPUs according to how loaded they are. And if we have one CPU that's very loaded and another CPU that's not, we'll take a little piece of work and move it over. The simplest algorithm in the world, and it does the job fantastically now that we don't have CPU and capacity coupled together.
Yeah.
Renen.
You wanted to say something?
Yeah, so you think about what Renen just said around taking some notes from the way that hyperscale infrastructures are built, and as he said, everything's fail in place. So the probability of having a lot of drives fail at one time is very low. And as you go beyond, let's say, +2 or so, as you start to build out the resiliency of the write stripe, you start adding exponents to the resiliency of the system. So you can build a system that has something in the order of, at let's say 500 plus 10, you're over 80 quadrillion years that we just calculated as the MTBF, which is a completely crazy number. And
An asteroid will destroy your data center first.
Right. And when we're comparing against the hard drive rebuild performance, we're not comparing against a hard drive stripe built from like 150 plus 4. You can't even do that. We're saying this is versus, let's say, like an 8 plus 2 style system. We're still able to rebuild even though our write stripes are so much wider. So the whole cost resilience equation completely gets turned upside down when you think about those types of MTBFs.
So in the 500 plus 10, if you write one data block within that stripe, you're actually writing that data block plus a 10 data
We
protection.
never write in place. We always write to new stripes. And that goes back to the erase blocks and not overwriting them.
So a new stripe would be yet another 500 data blocks from some other place, and you modify your metadata point to the new data block.
And
but it's not a log structured files.
It's not log structured because it's not cyclical in nature. We take erase blocks from wherever we can find them. And we choose the erase blocks. Again, we have this file system and retention built-in mechanism. And so we choose the erase blocks according to how many free write cycles they have. If I have a bin that says, this is going to be overwritten tomorrow, I want to put this on an erase block that has a lot of write cycles left. If I have,
You're
this is not
cognizant of the number of writes to an erase block?
Yes, and we do that without, at first, one of the technologies that isn't on that slide is host-based FTL. What's the other name for that?
Global flash translation.
Open
Channel.
Open channel. That is a technology that didn't come to maturity. In fact, the low-cost drives, the consumer-grade flash, are a lot cheaper than the open channel drives. So what we have to do is we have to fool the SSD into doing what we want it to do. Writing in full erase blocks is an example. The way we can monitor exactly what physical block is by always giving it one choice. The SSD will always be completely full except for the erase block that we want it to write.
And when a drive fails, we don't have to replace it with a like drive. We think about that just like we think about an enclosure. When we replace a drive, we just put some new device in the system based upon what's available at the time. So let's say we fail a 10 terabyte drive today. We can replace that with a 50 or 100 terabyte drive 5-10 years from now. And that's part of the warranty that we write for customers. We warranty the systems for up to 10 years. And you can do that because it's an asymmetric architecture.
Yes, and the nice thing there is, well, the analogy we like to give is of the human body. Every 7 years, if you look at our cells, it's not the same cells that were here 7 years ago, but it's the same us. We didn't have to refresh ourselves. We didn't have to forklift ourselves and put a new system in. And so parts of the system keeps getting added to it. Other parts will get removed from it, but the system is always up. What we've all been waiting for. Data reduction. So in most cases, what we described up to this point puts us in a place where we are competitive with hard drive-based systems from a TCO perspective, total cost of ownership. Our system takes up a lot less space, a petabyte in a rack unit, less power, less cooling. We guarantee it for 10 years because it doesn't have any moving parts in it, so it doesn't break. So you can amortize that over a longer time period. You can take all of your different tiers, and the average is what you need to calculate against. All these tricks we don't like to do. We don't like the customer to make these calculations. And so we want to be less expensive or on the same level from a TCA perspective, total cost of acquisition. When you give us that check, it shouldn't be bigger than the check that you would have given the hard drive vendor. And for that, we needed another mechanism, and we couldn't help ourselves but to build it because it's so cool. I want to mention also on the data protection is that it's based on a concept called locally decodable codes. What does that mean? We have a full stripe, a very wide stripe that we encode, but when we want to recover something, we only decode that piece. We don't need to decode the whole thing. This is also based on locally decodable codes. This is also possible because of this global view that we have from NVMe over fabrics, because of crossplane, and because of some new algorithms. So how has data reduction been done until today? Compression and deduplication. We don't do any of those. The reason we don't do any of those is because in most cases, the data that we get put on us doesn't compress and doesn't deduplicate. Unstructured data, unlike VDI or unlike databases where you have exact copies, you don't have exact copies of the data, and so you'll never find two blocks that are identical, and so the data does not deduplicate. It doesn't compress because if it did, the application would have already compressed it, and if the application already compressed it, then it doesn't compress at the storage level. Compression is a local process done at the block level or at the file level. The application can do that very well, and it's fine granularity. It goes all the way down to byte ranges to find commonalities and get rid of them. Deduplication is a global process. The storage can do that very well, but it's coarse granularity. You have to have full blocks that are identical in order to get it. What we did was look at the data. Again, talk to customers, look at the data, go out into the field. And what we found was that unstructured data sets have a lot of commonality across the namespace, whether it's genomics or images or log files, pretty much anything. I'll give the genomics example. My genome and all of your genomes are 99% point something identical. They don't compress very well because evolution has introduced a lot of entropy into our genetic code. And the parts of them that do compress well, the application has already compressed. They don't deduplicate because we'll never find a full 8K block or 16K block that's identical in my code and in your codes because the differences are slight. The mutations are at byte level granularity, in some cases even smaller than byte level granularity. However, when we look at it in human eyes, they're 99% identical. And if we have 10,000 of those in a data set, that's a lot of potential for data reduction that isn't being realized by this and isn't being realized by that. What do? We basically, again, break the trade-off. We go all the way down to byte level granularity, but we do it at a global scale. If you can imagine, we're compressing the entire namespace. However, when we want to read something, we only need to read that piece. Again, locally decodable codes. How does it work? We take all these blocks in the system, and we do variable size block, but that's not very interesting. And we do the sizes or the cutoff points according to the data, but that's not very interesting. A lot of other companies do that as well. What's interesting is that we don't look for identical blocks because we don't expect to find them. What we do look for is similar blocks. And similar is defined as such. If I have 2 blocks, and I compress each of them individually, and if I take those 2 blocks and compress them together, will I gain anything from that? How much will I gain? If there's similarity between those blocks, and I compress them together, I should gain a lot. And we've built our own similarity functions such that we can run a hash function on a block, and it gives out a number. We run a hash function on another block, it gives out a number. If those 2 blocks are similar, that number will be the same. And that is the new algorithm, the new math that was required here. What do we do with that data? We cluster all the similar blocks together, and then we choose one of them to be a reference, and we just save the deltas of all the other blocks against that reference. And so if you have 10,000 human genomes, and this block represents a specific gene, they will all be clustered together. This will be the reference, and the rest of them, we only keep the differences from that one. In effect, going down to byte-level granularity, but across the entire namespace. It doesn't matter where those blocks came from.
What happens, Renen, when people write encrypted data to your platform?
So if it's encrypted and it has different keys for each piece of data, this won't find anything. If it's encrypted, we coined the term similarity preserving. So if the encryption is similarity preserving, let's say you encrypted 2 similar things with the same key and they stayed similar to each other, this will work.
I guess that's fine. But if the application's encrypted all the rest of the time.
So I'm saying if the application has encrypted a lot of similar data with the same key, maybe it remains similar. If it's with different keys, there's no way it remains similar, and this will not work. What we will do, we don't have this in the product today, but it's part of the rest of the year's roadmap, is we will enable the application to share keys with us such that we can decrypt it, do our thing, and then re-encrypt it back. The same thing you have with compression algorithms. Some of them are similarity preserving. The application compressed it. We'll still find similarities if it compressed similar things. Some of them are not. So Lempel-Ziv is similarity preserving. Huffman is not similarity preserving. In those cases, if the application used it, we will need to de-Huffman, do our thing, and then re-Huffman when it reads out.
And this is done at the
C-node level.
container.
The container level.
Container level.
In real time.
It's really CPU intensive, or it's
It's CPU intensive on the write path. And what you remember is that we don't care about how much time it takes on the write path because we've already acknowledged the application. So many people ask, is this inline or is it post-process? That was the big debate on data reduction mechanisms. It's both, or it's neither, depending on how you look at it. It's post-process from the point of view of the application. It got acknowledged way before this happened. But it's inline from the point of view of the Flash. It didn't get written to before this happened, so we don't waste any writes.
So the acknowledgement on the right occurs when the data is in SCM.
Correct.
Sometime later, it's deduped before it's actually written to Flash.
Exactly right. Exactly right. And it's CPU intensive on the right. If you remember what we discussed, these workloads are moving more and more into a read-heavy state. If you write something once and read that thing 10 times, that's a 90-10 on a read-write pattern. In most cases, we see things getting read a lot more than 10 times. And so taking a little more CPU power in order to get this is a lot cheaper than buying the extra flash. Just as an example, if this is twice as computationally intensive as something else, and 5% of your IOs are writes, you basically need to pay 5% more for your CPU, which is cheap, rather than pay 5, 6, 7 times more for your flash, which is.
Yeah, the acknowledgement occurs when it's in the first. Do you replicate the data, triplicate the data in SCM across 3 different drives, 3 different JBOFs,
Again,
3 different.
topology awareness, such that we try. Oh, I didn't cover this actually. Good.
You have one JBOF, it's 3 devices in the JBOF. If you have 3 JBOFs, it's 3 JBOFs.
I got you.
Because this is in the case of storage class memory, but in the case of Flash, we also try to build our stripes across as many enclosures as we can. And if you have a single enclosure system, then it's no single point of failure, you're okay. and obviously the stripes are horizontal inside that system. As you add more enclosures, the stripes become vertical, such that you can lose a full enclosure, even though that's multiple failures, and still have enough redundancy to recover.
Is there a lifetime for data residing in SCM?
I don't know internally. If there is, then that controller refreshes the data as it needs to.
So the SCM is 1% of the total capacity, approximately? So how do you ensure that the SCM is never full?
So we use it for a write buffer and a metadata store. The way we ensure the metadata store isn't full is by allowing it to spill over into Flash. The write buffer, the nice thing about it, is that it's very different than other write caches. In existing architectures, the write cache can get full or empty depending on how fast you're writing to the system. That is because it has more bandwidth coming into it than going out into the media that's behind it. The Flash devices have thousands and thousands of PCIe lanes. We have more bandwidth going into the Flash than going into the storage class memory. And so it never gets full.
Yeah, okay.
Yeah, but don't you have a problem with the CPU? So if you don't have enough containers in the front end, then it becomes again a bottleneck.
Then you have less performance. So more of that CPU power will be doing the migration process. Less of it will be available for front-end IOs.
Is there any way to report like where a bottleneck would exist, whether it's not enough containers or whether it's something else?
Sure. It's not enough containers.
Fair enough.
That's the report.
Well, I guess, so I mean, from
99% of the time.
Yeah, from an administrative standpoint, I guess, could it be faster? I mean, obviously it's faster than what I currently have today as an example. Could it be faster by putting more containers and displaying that in some way?
Yeah, so the way it's displayed is by showing the CPU utilization of the containers. If it's at 100%, add more containers.
Okay.
If it's not at 100%, call us because something weird is happening.
Okay.
Usually what's happening, and this has happened a few times, is the tests that the customers are used to running aren't fast enough to saturate the system. And because we're displacing hard drive-based systems in most cases, then they need to redo their tests in order to get to a point where they hit our limits. This is one type of system. Another type of system, one type of customer. Other types of customers are very good at hitting the limit, and those are the types that we like.
But the statelessness of the architecture and the fact that we build in Docker means that we can very closely couple in with orchestration systems such that this can all be automated in your data center. Once we expose that you're near that 100% threshold, it can just automatically spawn a few new servers by talking to, let's say, Kubernetes.
That's weird.
Yeah, it didn't resolve so much.
It looks better here than it does up here.
There's a little too much glare, that's all.
Basically, you have the old pyramid on the left side, and you have the new pyramid, or lack thereof, on the vast side. So this is past, and this is vast. Anything that needs 10 microseconds of latency or 20 microseconds of latency, that's not us. That's something that you want to put very close to the CPU. That's something that we expect will be in memory or in DIMM form 3D crosspoint going forward. Anything that can live on sub-millisecond, all the way down to anything that you ever want to access again, put on us. And it will make your life simpler, and it will make your applications a lot happier.
I have another question about it.
Of course.
So when you told about the failures of the drives, okay? So you lose the drive, and then after that you told something about warranty or whatever. So can I replace the drives? Because if I lose 10 terabyte drives or...
Everything is hot swappable in the
They are
system.
also, but I can swap the drives.
Of course.
Of course.
Of course.
So it's not that I will go in
Everything
6
is
months
hot
from
swap.
now in the data center, and in the meantime I lost 100 terabyte out of my petabyte.
You can replace it as fast or as slow as you would like. If you have a lot of capacity, take your time. If you're up at the edge, go and replace it faster.
But hopefully we send somebody, and you paid support. But other than that,
No,
yeah.
that's okay even if you send the drive, but actually I don't want to lose my capacity.
Yeah.
That could be a problem. because I paid for 1 petabyte, and after
Yeah,
some time,
you can replace the drive and get the capacity back right away, or you can decide that you want to be a hyperscaler and wait till 4 fail.
we are all hyperscalers when it's time to buy, but then when it's time to operate the system,
None of us are, yeah.
yeah. So.
I like that sentence. I'm going to use it.
Software updated? I'm assuming.
Okay.
Throw away the containers and deploy new ones?
That is exactly right. In fact, the first piece of software that was written is a messaging platform that allows different versions of the software to talk to each other. And so you can upgrade each of these containers independently. Once you've upgraded all of them to the new state, then they will start reading and writing the new metadata structure in the new versions. And that's how it's done.
This is the extreme I/O experience.
Yes. We have people on the team from various companies, and we tried to take the good parts of what
Leverage
we know
that experience.
and not redo the not so good parts of what we did in the past.
Can you tell us whose QLC drives you're using?
We use whichever is cheapest. Whoever gives us the cheapest price, every quarter we negotiate, we go with the cheapest vendor.
But we were trying to work out that, and we can't think that there are any QLC NVMe drives that is, say, in a U.2 format available.
Oh, there sure are.
A, there are. B, as I said before, we can also support the M.2 form factor.
It's the Backblaze model. Just get the cheapest thing we can get our hands on in this form
Yes.
factor.
We've designed the system such that the cheapest, crappiest SSDs that are out there today are overkill for what we need. And we take all of that up in software, and that's what we want to do.